Today's lecture will be a bit more open-ended and free-flowing, so please feel free to just stop me and jump in. I think some interactions today would make the discussion much more lively. So we ended the last lecture, sort of talking about, we started talking about this issue of statistical computational gaps, and as Mohit was referred to right now, how do you get evidence for these things? So I want to briefly touch upon this topic and talk about it in the context of one particular example that I feel a bit more comfortable with, but now there are quite a few examples that have been explored in this domain. Okay, so to give you a sense of what is involved here, right? So let me start with another one of these spiked matrix problems because it's close to what we have been discussing so far, but I'll change the nature of the spike. So I'll say that I observe it's not good. So I observe some matrix M, which is lambda on n VV transpose plus W. W again is symmetric Gaussian noise, so Wij for I less than j are IID normal 0 1 over n, and Wii these are IID normal 0 2 over n, and everything here is independent. So for the spike V, the entries will now be slightly different. So VI's are IID either 0 or 1 with probability some rho, and this is with probability 1 minus rho. Okay. So roughly what this means is that you have some matrix that you observe. It's a symmetric matrix. There is some hidden principal submatrix where the mean is elevated to be lambda over n, and everywhere else it's 0. Right? But of course I draw it because this is the only way that I can draw it, but this principal submatrix doesn't need to be contiguous, right? The picture is like this only after I rearrange the entries in some way. Okay, so this is like some Gaussian version of the planted clique, sort of. You have some hidden submatrix where the mean is higher, and you would like to recover the support, right? So and then for us the recovery metric will still be weak recovery. So does there exist some estimate v hat such that if I look at 1 over n inner product of v and v hat, then this is bigger than some little absolute constant times rho. Okay, so let me say, okay, so C is some absolute constant. You know, 0.01, 0.001, something like that. And so when is this problem of interest? So this problem kind of comes from these applications known as sparse PCA, sort of. And the most interesting regime is when rho, let's say, is a constant but very small. So when you're thinking of this problem, think of sort of an iterated limit where first n is very large and then rho is very small. So you have some large matrix and you have a very tiny submatrix hidden, and you're trying to recover the support, right? And I set the recovery metric up in this form because I'm trying to recover a linear proportion of the support. That's my metric. Okay, any questions so far? Okay, now one remark first is that you have this matrix M, and you can say, well, is the signal at all perceptible? Can I even detect the presence of the mean, or is it so small that it always gets hidden, right? So there's a question is, okay, can I detect first the presence of the signal. Right. So turns out actually detection is easy in this setting, simply because I can look at the quadratic form 1 transpose M1, which is basically saying I take the matrix M, sum over all its entries. And so if I do 1 over n times this is basically lambda over n squared V transpose 1 squared plus 1 over n squared 1 transpose W1. 1 over n. You can easily check that this term is just one Gaussian that goes in probability to 0. Its variance is very tiny. And this term basically will behave like lambda rho squared. Okay. And so therefore, if you give me this matrix, I can at least immediately test and say that there is a hidden submatrix. I can always be confident there is one such thing. It's not pure noise.
Sorry, but assuming something about lambda, right?
For n, lambda is a constant, of course. Lambda will always be a constant, right? I should make that clear. So when I talk about this problem, the interesting regime, so the regime that I'll look at is that lambda positive is a constant, rho is a constant, and sort of small. And I'll basically always try to understand how large lambda needs to be as a function of rho when rho goes to 0. That's sort of how I'll try to understand things, right? Okay, so what about recovery now?
So, sorry, so when you say rho is small, it's a smaller order of 1 over n?
No, not as a function of n. So I'm really thinking of an iterated limit. First, n will go off to infinity, and then rho will be going off to 0. But rho, people have also looked at the version where rho goes to 0 as a function of n. That has also been examined. The results are basically the same. But I'll restrict myself to this case. Okay. So what about recovery?
Good question. So you said you'll think of lambda being a function of rho. Then does that mean that lambda should be 1 over rho square for detection?
This is going off to 0 in probability, right? This is a positive constant as a function of n.
N, okay.
Right? So here for any given lambda and rho, I can get a threshold beyond which if I reject it.
What I wanted to ask was, you said that you'll think of, first you do this n going to infinity.
Yeah.
Then you'll let rho go to 0 as a function of lambda, and you think of lambda
as a function of rho.
In that setting, I'm asking if we should think of lambda as being 1 over rho square for detection.
You don't, if you give me any function of rho, right, this will always be bigger than 0 as a function of n, right? Okay. So I can always detect. But yeah, there's this double asymptotic here which creates a bit of a confusion, but this term goes to 0 as a function of n, so things are okay.
That's good. The n squared Gaussians, right, over there?
Yeah, but W's have variance 1 over n.
Okay.
So they are themselves tiny, so if I look at this term, for example, it's like a Gaussian of variance n, so that's like root n times a standard Gaussian, I divide by n, so things are small. Okay? Good. Okay, so what about recovery? So here is the result. Oof, we're running out of pens. I think there's a lot there as well. Okay, I think we have enough. Okay, this is great. Okay, so first result is that if lambda is little o square root 1 on rho log 1 on rho, this is square root as a function of rho, little o as a function of rho, then it is information theoretically impossible to recover a linear fraction of the support. Okay. So let me write down what these thresholds are here. So here I have this point square root 1 on rho log 1 on rho. Okay. And roughly, if lambda, which is the signal to noise ratio parameter for this problem, if it's smaller than this quantity, then okay, you can never recover a linear fraction of the support. Okay. If lambda is bigger than some big constant, let's say, times then the MLE recovers a linear fraction of the support. Okay. So yeah.
So just so if I'm doing my calculation just to this, so even if you go below this regime, you can actually detect the signal. You just can't find a linear fraction of the signal.
Yes,
right? Okay.
yes, that's all.
Okay.
You can definitely detect.
Yeah.
It's all, you can always detect, but if you're trying to really do the recovery, then that is hard now. Right? Okay. So this is a purely information theoretic result, right? It says that this is roughly how large lambda needs to be as a function of rho so that I can actually recover a linear fraction of the support. Okay, good. So now comes this question that, okay, so what is the MLE? Unfortunately, so the note here is that roughly because you have n times rho many, the size of your submatrix is of size roughly n times rho. So solving the MLE is basically like solving the supremum over x in 0 1 to the n. Sum over xi is n times rho x transpose mx, right? And so argmax, let's say. But of course, we can't really compute this in practice, right? This involves searching exhaustively over all n-row sized blocks. So this is computationally infeasible. Okay. So how well do our favorite efficient algorithms perform? Right?
Question.
Yeah.
So for the first part of the theorem, is it a small o notation or big O notation?
It's small o.
Now how about lambda is the same order of the...
Right. So yeah, I know that, okay, so I don't have the result which is sharp at the level of constants. I think here C needs to be basically like 2. I think that's the right constant. But I don't have a negative result that, oh, if it's like 2 minus epsilon, then I can't do it. So there's some gap here. Okay. But roughly in terms of order, this is the right order. Yeah, I don't even know if the transition is really sharp or not. At least I know that there is some large enough constant for which it will work. Okay. Okay. Right. So what about our favorite algorithm? So let's say spectral, right? So what about spectral? right? And okay, the naive spectral algorithm is basically like, okay, at least the naive spectral algorithm is basically set x hat to be the argmax of x transpose mx subject to L2 norm of x is equal to n times rho, right? Something like this. And so we can actually analyze the performance of this estimator using exactly the behavior of the top eigenvalue for the spiked random matrix that we saw a couple of lectures ago, right? So in particular, if you see this, m is basically lambda over n v transpose plus error. So I can write this as lambda rho over n times v v over square root n rho, v over square root n rho plus w, right? So now I've normalized this to be a vector with norm 1. So essentially our random matrix results essentially say that top eigenvalue is an outlier if lambda times rho is bigger than 1. Okay? So, or effectively lambda bigger than 1 over rho. Okay? So out here somewhere far is lambda equals 1 over rho, right? If lambda is actually bigger than 1 over rho, then even if I do the top eigenvector, that will have some linear correlation with the planted truth. Okay? Okay, so what happens in the middle, right? This is kind of where the mystery is. And how do you, if you believe that in fact nothing will work, how do you even, try to get some evidence for that? At least in the context of estimation. So one idea, and I think this is kind of the driving philosophy essentially in this entire endeavor, is that you can somehow try to get, try to show that, let's say, somewhere in this regime, broad classes of algorithms won't work, right? And the more algorithms that you can rule out, the more evidence you have that this gap is actually something quite fundamental. That's kind of the idea.
So actually, I have a question before we go. How does one then prove that the MLE will, because it's like, how will you?
Oh, this is like basically an existence proof. So this is like a probabilistic method kind of proof.
Okay.
Something like, yeah, in that flavor. It's a bit different because you're working with Gaussians, but effectively it's like first moment, second moment, that kind of result. Yeah. So it's some kind of maximum, so you basically prove that you search over everything, take a union bound, get something. So this is purely an existence result. Okay. So the idea is show that large classes of algorithms do not work in this intermediate SNR regime. Okay. So how do we do this? So I'll try to convince you that you can at least prove that certain classes of Markov chains won't work. Okay, so what I'll try to show is that sum, and sum is very much emphasized, local Markov chain algorithms do not work. Right. And my result will be quite weak in that I won't go all the way up to 1 over rho. So I'll only rule out somewhere, you know, something here in the middle, roughly. But okay, some evidence. But that I think is mostly a proof artifact. But let's see. So what do we do? Yeah.
But then, so you said people have ruled out large class of algorithms, and
Yeah.
all of these rule out all the way up to lambda equal to 1 over rho.
So whether you can go all the way up to lambda equals 1 over rho, I think now becomes like proof specific. So for every class of algorithms, you can go up to a certain point. There are proof difficulties that you run into. I think generally for this problem, I believe that lambda equals 1 over rho is the right dependence. But whether you can go up to that or not with your proofs.
Or conversely, nobody has any algorithm that works below 1 over rho.
Probably, or candidately.
Probably, yeah.
Yeah, that's the.
Yeah, then you wouldn't even do
Exactly.
all of this.
Yeah, then-
Why
then-
would you go into this? Yeah, yeah. No, but local Markov chain algorithm, do they even work? Before we try to show that they don't work, at least.
Right, so that's a very important question, and I think that is actually one of the important questions in this domain, that there are now, over the past 3-4 years, quite some tools that have been developed to rule out Markov chain algorithms. There are considerably fewer tools to prove positive results about Markov chains, which is annoying. Which is really annoying, and I think it is very important to develop more tools for positive results for Markov chain based methods. And so you might even say that, you know, I rule out Markov chains, but maybe Markov chains are like a really stupid class of algorithms, right? But what I'll try to convince you of is that the way we rule out Markov chains, we actually explore something which is a bit more intrinsic to the problem. We'll actually look at the likelihood landscape itself, and that will rule out Markov chains. So I think the fact that the likelihood landscape behaves in a certain way provides some intuition that it's not something just about Markov chains. There is something really interesting that's happening in this problem, which can potentially be a barrier for other algorithms as well. Okay?
So one more question. So whenever we're thinking of negative result, I like to think of the analogy with P versus NP completeness and so on.
Okay.
So here there's so many results ruling out large class of algorithms. Is that how it evolved in complexity theory? Did people, after the NP completeness, did people kind of rule out many classes of algorithms?
I'm not much of an
I don't
expert.
think so. Like, of course, but there are some problems for which you can't prove hardness results, right? That's what maybe we were briefly discussing before that.
And these types of
So
hardness
I-
are different, I guess, right?
Yeah, it's average case. That's
Yeah, yeah.
sort of very
No,
important.
it's not the same.
Yeah.
I'm just thinking of an analogy.
So the analogy is more into reductions. Like, for example, that's what briefly we were talking. Maybe you would say, like, he's talked about so many problems where the gaps is, you might want to say if there is, the gap for this will be there.
Right.
Then there is some gap in
This
some.
gap, something else.
Something
might be
else,
there.
yes, yes. So the reductions, this analogy and that work is happening, but this kind of ruling out was not done in the worst case world?
No, because people were just coming up with algorithms all the time, right? Like we didn't know what the landscape was, right? Yes.
You're saying you guys are more optimistic.
I don't know.
than
Yeah.
pessimistic?
No, I think that's definitely
I
true.
am more optimistic.
Okay, so what do we even look at, right? So I'll look at the. So the idea is to actually look at the likelihood landscape. Landscape. So what is this thing? So I'm saying that I'll look at the maximum. So I'll maximize my likelihood over vectors that are, you know, feasible. So these are and then they have a certain overlap with V. Okay. So roughly, in terms of the problem, you can imagine that here is the real submatrix. You're only taking the maximum likelihood over principal submatrices that have n times delta many rows and columns common with V. Right? That's what I'm doing. Now, obviously, this is not something that I can actually implement on a computer, right? This is purely a theoretical device that can help me understand the problem better. This is not something I can calculate on the data. So, turns out that for every delta, this will converge to some limiting object f of delta. Okay. And we can actually now investigate the behavior of f of delta as a function of delta. Question? Fine. Okay. So delta can basically go from 0 to rho, right? My submatrix can either have no overlap with the planted truth and up to rho overlap, and it's exactly the same. And if I initialize at random, okay, so even if I didn't look at the data at all and I just gave you an n row sized submatrix, I would get about rho squared many rows and columns in common, right, purely by chance. So rho squared is kind of the interesting thing to look at. You know, can you do better than rho squared? That's kind of the interesting question. Okay, so now how this function f delta behaves is definitely a function of lambda, right? Depending on how strong the signal is, the function will behave in different ways. For example, you would naturally expect that if lambda is very, very large, so okay, there are two extreme cases here. So for example, if lambda is exactly 0, then the global maximum of this function should be exactly at rho squared, right? You have no idea about the signal. Whatever is your optimum has basically nothing but trivial correlation with V. So this function should basically look like this: global maximum at rho squared and then decay. Right? That is how this function should behave. The other extreme, of course, is that if lambda goes off to infinity, right, then at some point you'll kind of recover the entire matrix itself. So now if you look at this function, I think it would look something like this maybe. So the global maximum would be very close to rho, right? Make sense?
Can you repeat the rho square, where rho square comes from?
Yeah, so I take my matrix, I know potentially there is this n times row sized submatrix that's hidden. I want to come up with a guess. I don't look at the data at all. I just give you a random n times row sized subset. And so now I look at how many I will get common, just by chance. And that will be rho squared, right? So the entire question is, what is it better than rho squared or not? Yeah, I mean, I don't really care about what happens below rho squared because, okay, that's potentially not where everything interesting is happening. So what I'm trying to convey through these two pictures is that the actual behavior kind of depends on how large lambda is, right? Okay, and so in terms of this quantity, which is sort of the restricted maximum likelihood, what this theorem is telling us is that if lambda is actually bigger than some c square root 1 on rho log 1 on rho, if this is what is happening, then at least I know that the global maximum is at some point c times rho. Right? That's what this is telling me. The information theoretic result essentially says that if lambda is bigger than this, okay, I don't know what happens at rho squared whatever, all I know is that the global maximum is here. Everything else must be smaller. Make sense? Because I do recover a linear fraction, so my global maximum must be at c times rho. Okay. So now what can we say? So so what we can do at the moment, or okay, there are finer results now, but suppose I look at lambda which is bigger than and actually much smaller than some half plus epsilon. Okay. So this is lambda that is much bigger than the information theoretic threshold. So I know that the global maximum is at some point c times rho. That I know. What we can show, at least in this window, is that roughly you have some local maximum very close to rho squared, then it dips, and roughly sort of, okay, I don't know what happens in the middle, but it kind of gets to a global maximum at c times rho. This is kind of the intuitive picture that we have. I actually don't know what happens in the middle. It can have other local maxima as well. But at least I know there is one local maximum here, somewhere very close to rho squared, and then the global maximum is at some c times rho. So what is this telling us, right? This is kind of telling us that if you look at those submatrices that give you a high value of the likelihood, let's say higher than this particular dotted threshold, then they either must have, you know, a certain high correlation with the planted hidden submatrix, or they must be kind of very small. You can't have something in the middle. Okay? That's what this non-monotonic picture gives us. And once you, okay, so this picture is actually something that's that is pretty interesting, because it really says that there is something rather interesting that is happening in this problem, particularly in this signal regime. Okay.
So this picture that you are showing, so how does this translate to the geometry, like the
right.
that you
So what that means is that I have some hidden matrix, right? Suppose, without loss of generality, that the hidden matrix is at the top corner. What this is saying is that if I need to get some likelihood value that's higher than this threshold, either I can get it with a very small overlap, so I have, you know, a very few rows and columns that I have common with the hidden one, or I actually end up recovering a lot. I can't get such a high value of the likelihood by actually having an intermediate number of rows and columns common. That's what this is saying.
And is there any intuition why is this peak around rho square?
Right. So why is this peak around rho squared, and what is the intuition for this? The intuition for this is that the maximum number of submatrices essentially have rho squared correlation with the hidden truth, right? That's where the entropic maximum is. And the more you correlate with the hidden submatrix, the more you gain in terms of likelihood from this hidden part, but the more you lose in terms of entropy, because there aren't as many submatrices. So there is a real fight going on between how much you gain in terms of the likelihood by having more overlap with the hidden submatrix, but you lose in terms of how many matrices there are, right? Because I'm looking at the maximum, so how large the maximum is really depends on how many random variables there are.
I can view this overlap as, like, let's fix the overlap with this corner box,
Right.
and then optimize the remaining part of our entire this random.
Exactly.
part.
That's what this function f delta is doing, right? Yeah, the issue is that we can't really go much beyond this because this function f delta turns out to be quite involved. In our case, because delta is rho is like a constant, this is difficult to track. Other people have looked at, so there is a follow-up paper by Gerard Benarous, Ilyas Zadik, and Alex Wine, who look at the case when rho is going to 0. But there they run into sort of issues with doing first moments and second moments. There are some technical issues why I think often you can't really push it all the way to 1 over rho. But this is sort of, I think, the picture that emerges when you look at objects like the restricted likelihood landscape, right? And it's a consequence of this picture. So this allows us to actually prove that if I run a Markov chain, let's say, so one way in which I could try to recover it is to look at a distribution, some distribution which mu of x is proportional to e to the beta x transpose mx, where beta tends to infinity, right? This would be like a Markov chain, so I take it with beta very large. This is a distribution that kind of tries to sample from those submatrices that have very large values of the likelihood. And so if I do something like a local Markov chain with mu as stationary distribution, then these Markov chains are stuck. And the entire idea is, with Markov chains, you kind of see that, okay, if I was around rho squared, if I have to get to this point, then I have to actually decrease to a much smaller value of the likelihood. That's like a bottleneck on my state space. I get stuck. Okay. Questions? Right. So, and this is sort of going back to, I think, the point that Mohit raised, which is that, okay, yes, we managed to rule out some classes of MCMC algorithms. You can say, okay, maybe I don't really care about MCMC algorithms. They are probably not really powerful ones in the first place. But I think the result for MCMC essentially comes by looking at certain structural characteristics of the problem itself. And I think that kind of suggests why this might be hard for other classes of algorithms as well. Okay.
Just to understand, so this MCMC algorithm will indeed find the maximum, but it will take a very long time.
Exponential time, potentially. Yeah, because if beta is large enough, then if you look at a typical sample from this will basically look like something that has linear correlation. The mass essentially lives here. It's just that if you initialize it somewhere here and if you run it, you'll essentially get stuck.
So can you repeat what you said about the landscape? You said we have 2 peaks. And we know that we have 2 peaks.
Yeah.
And then what is it that we don't know? We don't know what's happening in.
We know that at some point beyond the first peak, it's lower. That we know.
Okay.
Are
there more peaks in between?
This I don't know. So my picture here is a bit uncertain in that I don't know if it has more local peaks or not. But that doesn't really. To derive the negative result, having just 2 different peaks and a dip in the middle is enough. But the picture could be more complicated. There could be other things. Okay, so for this particular setting, there has been quite a few investigations, and the results kind of match. How much of this window you can cover, I think, depends on the specific regime and the specific class of algorithms that you're trying to rule out. So I think these results that I described, these are from a paper that I had with David Gamarnik, Akash Jagannath, and myself around 2019. But following up on our work, there were quite a few other investigations. So there was a paper by Gerard Benarous, Alex Wine, and Ilya Zadik, who actually look at the case when rho is going to 0 as a function of n. And then I think this was also later, that 20, I would say. Okay, the year I have to check, but they looked at the case when rho n goes to 0 as a function of n, and they have finer results about the Markov chain as well. So they really relate how long it takes the Markov chain to the depth of this dip and things like that. There were investigations by Barbier, Macri, and Cindy Rush, are also in the same year, who look at AMP algorithms under rho n goes to 0, and they find that these algorithms essentially will also not work. And finally, there has been sort of one very interesting breakthrough, I think, in this area. So there is a paper by Alex Wine and Salil Shram, I think around the same time, where they rule out low degree algorithms. So they essentially show that if you have some algorithm which is a low degree polynomial in terms of the matrix entries of M, then even if the degree is low enough, then this will not achieve a high correlation, or they won't be successful. So this result, I think, is super nice because it rules out, in principle, a much larger class of algorithms. It's not tied particularly to Markov chains or things, right? But I think so far their method is very much tied to this spiked matrix setting, but I think there are some very cool ideas here. Okay. Any questions? Okay, so I should say, okay, so let me say a few more things here. So I sort of grounded this discussion in the setting of estimation, right? And I was showing, how you would go about ruling out certain classes of algorithms in the context of estimation. There is also a certain an analog of this question in the context of detection. So can you actually detect the presence of the signal using a computationally efficient algorithm? And actually the detection question has been much more tractable. And there is a, okay, so let me say something about that. I won't go into too much depth, but I can put in a reference which I think could be interesting to follow up on. So so the note here is that there is a similar question for detection, right? And it's kind of similar. You will have, the picture is kind of similar. You have some information theoretic threshold for the SNR parameter, below which you cannot detect between the signal and pure noise, and then typically there is some algorithmic threshold that's conjectured, above which there is a simple test, and okay, you want to know what happens in the middle, and you want to provide the evidence that nothing really can work. So one thing that has come up in the context of detection is this method, is this so-called low degree likelihood method. This originally came out from the work of Hopkins around 2017, and there is a very nice survey on this by Tim Kuniski, Afonso Bandera, and Alex Wine in 2019, I think. So this is a very nice survey which describes what this low degree likelihood method is.
This is in the context of which problem?
In the context of detection.
But for which part?
So for you, I mean, this you can examine the same question for many different planted problems, right? It's not tied to a spiked matrix kind of question. So the question is kind of emblematic. You can apply the same method to many different problems. For example, if you want a very specific example, you can look at a sort of cousin or sister problem to the one I have here. So you can look at this problem, but now I change the distribution on the VIs. So it's 0 with probability 1 minus rho, 1 with probability rho on 2, and minus 1 with probability rho on 2. Right? And I can then look at a hypothesis testing question where lambda is 0 versus lambda is positive. So this is, for example, a setting where even detection is quite hard. And there is sort of an evidence that there will be some hard phase in the middle depending on how large lambda is as a function of rho, right? And the picture that has sort of emerged, and this picture turns out to be quite robust, is that recall that this model is a completely Bayesian model. So this is a simple versus simple hypothesis testing problem. So the best thing that you can do is to do the likelihood ratio test, right? So best test is the likelihood ratio test. But the difficulty naturally is that computing the likelihood ratio can be difficult. It might involve kind of summing over all these discrete binary vectors, and that can be challenging and computationally inefficient. So turns out the conjecture in this area is that the best computationally feasible test you would get by projecting the likelihood ratio to a low degree polynomial. In terms of the input. So for example, you might say, okay, as a proxy for n to the d algorithms, I will only consider hypothesis tests that look at polynomials of degree d in the entries of the matrix M, right? So if I'm only looking at hypothesis tests that decide, to reject the null based on polynomials of degree d in terms of the matrix M, turns out, and this is completely rigorous, that the best test will look at the projection of the likelihood ratio to the space of degree d polynomials. And okay, if you look at that test, you could see that those things will not work in this intermediate regime. So that's okay, some evidence again. Whether looking at that you completely believe that it rules out all n to the order d algorithms, okay, that's where kind of there is a jump. But this method generally has turned out to be extremely robust. It turns out to be quite tractable. You can use it in many different contexts, and typically the predictions from the low degree likelihood method are consistent with other evidences that we have. So nowadays it has become, at least in this area, it has become quite common that if you run into a new problem and you're trying to predict what the algorithmic threshold is, you basically look at the low degree likelihood method and try to come up with a prediction for what the algorithmic threshold would be. Right? So I won't go into too much details regarding exactly how the method is implemented and how it looks in specific examples. The survey of Kuniski et al. Is a very nice place to look at this. Okay. Any other questions? Okay. So
may I ask a question about the recovery?
Yes.
So when lambda is large, you mentioned the maximum likelihood will recover a linear fraction of the support.
Right.
So, but normally, based on your argument, you recover larger space. So can we talk about some statistical inference? Say which area we are recovered on, we feel more confident. Is a true signal. Which area we recover is less confident?
Yeah. No, that's I think a harder question. Definitely. So there is definitely this question of like, once I have this estimate v hat, can I actually use that to infer something, to do something about the support? I don't think we have very good results on that front yet. I think it would involve, taking this estimate v hat and somehow debiasing it so that for each coordinate you can do some inference. So for example, the paper of Montanari and Venkataramanan that I was talking about in the last lecture, they actually outline some applications in the context of like FDR control and things like that. So it turns out using the state evolution machinery that I described yesterday, you can do certain things. But if you care about single coordinates, FWER control, I think you would need a bit more. But at the level of FDR, I think you can do something. Okay, so let me take some time to talk about a few problems that I find very interesting. And I should say this at the very outset that these are problems that just I'm personally very excited about, and I do not mean to imply in any way that these should be really important problems to solve in the area. I certainly do not wish to make that point, but these are essentially problems that I think would be really nice to have an answer to, and I do believe that in solving these problems we might need to develop some new tools which can be useful for general other questions in these areas, right? Okay, so the first set of questions, some future directions. So some of these are basically just in the context of even the contextual block model that I introduced early on. So contextual block models. So let me just recall the model at least for the k equals 2 case. So two communities, I have sigma I, which are IID plus 1 minus 1 with probability half. I have some latent U, which is normal, 0 I P on P, probability of an edge is A over N if sigma I is sigma J and is B over N otherwise. And I have these vectors bi at every node, which are like mu over n, sigma I u plus zi on square root p. Okay? So recall that the model is that I have a graph and some p-dimensional covariates at each node. I generate them using the same underlying randomness. So the graph is marginally just from the stochastic block model with edge probabilities a over n and b over n. And then the covariates, the node covariates basically are Gaussian mixtures. So if sigma I is 1, it's a Gaussian centered around u. If sigma I is minus 1, then it's a Gaussian centered around negative u, right? And u is a latent vector that I don't get to see. And the zi's are IID normal 0 identity, right? So this was our model. So what I described in a couple of lectures ago, and what I know at least in this setting, is the information theoretic threshold for detection and recovery, and I have some fairly expensive algorithm to perform detection and recovery in these cases. So one of the questions that I really care about is, you know, some spectral algorithm. For detection and weak recovery. Okay, so this would be kind of in the style of the non-backtracking matrix-based spectral algorithm developed in the context of just the vanilla block model and the results of Bordenave, Lelarge, and Massoulier that I described a few lectures ago. So what would be the analog of such a spectral algorithm in this setting? I think this would be kind of interesting to develop even from a purely mathematical perspective, because it seems to me that like the non-backtracking matrix based methods quite heavily use just the adjacency matrix of the graph, right? But here you would have sort of two matrices, one which you get from just the graph and one which you get by stacking the covariates, right? Some p by n matrix. And this is the adjacency matrix of a sparse graph. This is a dense random matrix. So the two objects tend to not play really well with each other. So I feel that even developing such a spectral algorithm, I think, will require some new technical ideas as well. But generally, I think having a cheap spectral algorithm that you could use for this setting would be really nice. Okay. So this is one question. A second question, which kind of goes back to something that actually Yajun asked me after one of the lectures as well, I think, is that so far I have been kind of skirting one issue under the rug, which is that whenever I have talked about, let's say, Z2 synchronization or community detection, I've always assumed that all these parameters are known to me. So lambda is known to me. The edge, you know, A and B are given to me and things like that. It turns out that at least in those problems, I wasn't really cheating. For example, in the context of Z2 synchronization, if I didn't know lambda, I don't really care, because in the regime so for Z2 synchronization, if lambda is bigger than 1, then my top eigenvalue essentially is somewhere out here, and I know it will be close to lambda plus 1 on lambda, right? So even if I don't know lambda, I can look at the outlier eigenvalue and I can just read off what lambda should be, and I can use that, and that's fine. Similarly, for community detection, if my threshold, you know, if I'm above this threshold, if this is bigger than 1, then you can count objects like self-avoiding walks and construct consistent estimates for A and B. So this was done in a paper of Moselle, Niemann, and Sly quite early on in this area. So if you're above the threshold in these problems, you can estimate the parameters and then just use the consistent estimates. It's fine. What I don't know, and I'm not quite sure how to go about it, is what happens in this problem. Okay, so how to estimate you know, mu A and B if I don't know them, right? So the question is, recall that the information theoretic threshold in this problem, I require one other parameter, so I kind of worked in this high dimensional regime where this goes to some constant 1 over gamma, and the IT threshold is that I need the average degree of the graph to be bigger than 1, and lambda squared plus mu squared on gamma to be bigger than 1, where lambda is the usual ks parameter, right? Okay, so suppose I'm in this regime, but I don't know mu A and B. Can I actually get consistent estimates and then just go about doing recovery in these problems, right? I actually don't know the answer to this question. It's for the longest time I believed that I'm just being stupid and that there should be something here which is, you know, if you just squint at it, it should be possible to do. Recently someone told me that they believed that it should not be possible. So now I'm very confused. But I think this is a easy to state question, but might have some interesting aspect to it. Okay, more broadly in this setting, the thing that I do not understand at all is the problem with k strictly bigger than 2 communities. So you can set up a version of this which is basically the analog of this, where your sigma i's are IID uniform on a set 1 to k. Your edge probabilities are still A over n if sigma I is sigma j and B over n otherwise. And you need now k of these cluster centers. And your BI will be essentially something like square root mu over n u of sigma I plus zi over root p. Right. So if I'm from the third group, then I observe a Gaussian point cloud which is centered around u3 roughly. And you can ask the same question. What about, what are parameters a, b, and mu for which I can actually do detection and weak recovery? This is not known currently. Of course, the analog of the Kesten-Stigum threshold, you can still count these self-avoiding walks and things, and so you can get some threshold of that form. But I think the precise information theoretic threshold should be really nice to have. Okay.
I have a question about the formulation. Here the sigmas are at so here when you drew the picture, there was basically two
something something around
u
u
minus u, but here there's a u1, u2, u3.
Correct. I'm just confused about the indices. Here we have +1, -1. Here we have 1, 2, k. Are we losing something there?
I don't think so. I mean, because I think I could have as well, set this up so that I had 2 centers, u1 and u2.
Oh.
I don't think things would have changed as much.
Okay.
I think here we were just doing u and minus u, but I think it's fine. I mean, if you want, you can kind of impose the condition that sum of the ui's is actually 0.
Okay.
That would impose the same condition, but I think even unrestricted, these are Gaussian, so I think the sum of k of them should be roughly 0.
Okay.
But if required, I think you can set that condition. Okay. But generally, I think this is something that, is not really understood at present.
I try to add a remark here. If the k is greater than 3 communities, so will the James-Stans estimation, those phenomena will kick in here? Simultaneous estimation.
I would say it's somewhat different because this, for example, in the context of James-Stein, right, you're looking at like a sequence model and a supervised problem in some sense. These are completely unsupervised problems, right? So it is true that for k bigger than 3, the phenomenon is kind of different, but I think it kind of manifests in a slightly different way. Okay. Okay, so a second theme of questions that I would like to remark about are questions related to universality of algorithms. Right. So far, when I presented all these results, I have always made very stringent assumptions on the distributions, especially on the noise, right? So in the context of Z2 synchronization, I have always assumed that things are Gaussian, the noise is Gaussian and things like that. And of course, many of you have already pointed that, okay, do I need Gaussianity? Is it really important? Of course, there are two sides to this question. The precise information theoretic threshold, of course, depends on what assumption I make on the noise. So if I change the noise from Gaussian to Bernoulli, the information theoretic threshold can shift. It can become way easier. So those are true. But at the level of algorithms, so if I look at the behavior of the largest eigenvalue and the eigenvector, if I look at something like AMP and these things, then there is usually much more robustness to the precise distribution of these entries, right? So this has been, a focal point of quite some investigations, and we know quite a lot. For example, in the context of spectral algorithms, let's say in the context, if you want a specific problem in these spiked matrix kind of models, it's well known that if the entries Wij are independent and sufficiently light-tailed, then the top eigenvalue eigenvector has same behavior. Okay, so that's at least good. So this is kind of well known on the random matrix side. Similarly, let's say for AMP algorithms, I think typically here you need a bit more. So if Wij at least has all moments, this is, I think, still required, finite, then universal. And I'll be happy to share references if you're interested. Do let me know. So for these algorithms, in certain cases we know that our Gaussian assumptions are not really important, and they are kind of only specific assumptions to let us analyze the specific behavior of these algorithms. Things that we don't know, I think, here. I think in the context of spectral algorithms, what happens if the errors are heavy-tailed? Okay, so we don't quite know much there. For example, you can ask questions about structured noise. So roughly what I mean by structured and dependent noise is that, if you have this matrix that has that is of size n by n, if you have IID entries or independent entries, then you still have order n square bits of randomness. What if it has lower amounts of randomness or a lot more dependence? What happens in these cases? So we have a recent result with Rishabh Dudeja, Yue Lu and myself. This is in the context of AMP algorithms. So we are able to show that under certain structured noises things are still the same, but you need something. But generally I think this is still a bit limited. And finally I think the variational inference results that I presented, especially the ones which tried to locally optimize the TAP based functional to do inference, for those arguments I think Gaussianity so far has been used very, very crucially. So if you have like IID sub-Gaussian noise, does it still work? I don't know. So I think generally in this space the main question is, can you go beyond the specific distributional assumptions that we've made so far and still prove that things are kind of robust, they stay the same. Or if they are not, then can you modify these algorithms so that you still get the same statistical performance, but it's robust to the distributional assumptions. Okay. Any questions on this? And okay, there's a third question that I want to state. It's, I think, kind of very simple to state, but it's not as closely related to the inference problems we've been discussing. It's close to sort of an optimization question, but I think it's still kind of really nice to state. So the question is as follows. I have my Z2 synchronization matrix, so it's lambda over n, sigma sigma transpose plus W. The sigma I entries are plus minus 1, right? Now what I want to do is the following. So forget the inference questions I've been posing so far. There is some value of the maximum likelihood, right? So the value of the maximum likelihood in this case is the max of V transpose MV, where V is this vector, right? Suppose I just want to calculate what this maximum is for whatever reason, right? This is something like a max cut-ish question. And I can't really calculate this, like, okay, if I do exhaustive search, that's not really possible. So now I want a certificate for this. So what is a certificate? A certificate for this is, you give me a matrix, something that I can calculate that will always be an upper bound to this ground state or to this maximum value. So to give an example of a certificate, I could always upper bound this maximum n times lambda max of m. Right? This is always true. And I know the behavior of lambda max, so this is n times 2 if lambda is less than 1, and lambda plus 1 on lambda if lambda is bigger than 1, right? So this is a certificate, and I want to do better. So to go beyond this spectral certificate, I can look at SDP, right? So in fact, of course, this is exactly the relaxation that we looked at. This is less than what I'll denote as SDP of M, where SDP of M is basically the maximum of Mx subject to x positive semi-definite, xii is 1 for all I. Right? This is exactly the relaxation that I looked at. So this is an optimization problem. Provably, it's always smaller than this thing, right? My question is, what is the behavior of this SDP, this value, right? What happens to SDP of M? Let's say 1 over n, because that's the right value. So we know something about this. What we know is that if you look at 1 over n SDP of M, so we know that this converges to 2 if lambda is less than 1. Okay, this we know. If lambda is bigger than 1, you can always prove that SDP of M is less than n times lambda max. This is always true again, deterministically. So that this quantity is less than equal to lambda plus 1 on lambda. And we know, actually this requires a proof, but we know that this is strictly bigger than 2. Okay? So if I draw the value of this SDP as a function of lambda, up to lambda equals 1, it's at 2. Then I know that it moves away, and here is the upper envelope. I don't know if there is a gap or not. This is less than equal to. Okay. So my question is, like, can we understand what the value of SDP of M is?
But you expect a gap there.
So, okay, I don't know. But the precise question is, at least there's an upper bound. Is this, for example, one first question is exactly as you say, is this upper bound a strict upper bound? Is this inequality a strict inequality, or is there potentially equality? I think it's kind of interesting because it would then provide an example where you can have a better certificate than the spectral certificate using SDP. And okay, if you can do this, then you can be more ambitious and say, okay, if I go higher rounds in the SOS hierarchy, can I do even better?
So the strict inequality, I guess, follows from what we also discussed. I guess, like, just because of weak recovery, we put this SDP gives, so but it can't be 2, yeah?
It can't be 2, but yeah, it requires some work because you have to construct like a witness. So you have to construct a specific X for which this value is like some 2 plus delta. So you have to take, as you say, there's weak recovery, so you take some part from the spike and some part from the noise, and you have to prove that it does push it away. So the reason why I like this question is that it's sort of similar to what happens to the largest eigenvalue. It's a similar phase transition phenomenon. It sticks at 2 and then it kind of moves away. The entire question is, okay, what should this value be? And then, whether there is strict inequality or not. Even I think the question of whether there is a strict inequality or not here, I think, is interesting. Okay. So I think these were the questions that I had, but if you have other questions, points to discuss, I'm happy to stick around.
So let's all thank Shubrata for the entire awesome tutorial.
No, thank you so much for coming to all the lectures.